to the organizers for inviting me to give a talk. It's really nice to give a talk in any venue, I think, about this. I really enjoy talking about it, and hopefully you'll enjoy listening. So I'd like to talk about the nonlinear Schrodinger equation. Oh, excuse me. And this is we're talking about the defocusing equation, and it's in 3 dimensions. And this, so I right now is an interval, any interval, but we're ultimately discussing global well-posedness from. So then, of course, I would end up being the whole R, whole real line. And I'll just briefly sketch out the scaling symmetries that we have for this problem. So as you know, just by looking at the list of names, there's a lot of people who know this already, but I'm going to just talk about it anyway. But we have a scaling symmetry, right? So we have U of Tx. And then if we had a solution U of Tx, then, we would have another solution for any lambda. For any lambda bigger than 0, we would have a solution. And you know, if the interval I was not all of R, then you would have to change the interval depending on what lambda you picked. But you know, in our case, we're going to end up talking about global. So then, of course, R would just be R in any case. But the scaling symmetry is really important because we get this critical Sobolev norm. It's H dot SC RD. RD is the dimension, and SC is going to equal D over 2 minus 1. So where does that come from? That just comes from your calculation of your norm. So you know, you have U naught, and then you plug in your lambda, and you calculate your H dot S norm, and it's equal to lambda to the S minus SC times the norm of U naught. Now, so, you know, if S equals SC, then you would have the norm wouldn't change, right? If you picked a lambda, you know, whatever lambda that was, the norm wouldn't change, and that's where this comes from. And by the way, let me just say something, because I've been teaching using the iPad too, and I find sometimes I accidentally will point to something, but not write it down or whatever, and then I realize, oh, I'm pointing, but nobody can see where I'm pointing to. So if you need me to, you know, stop me and say, hey, what are you pointing at? You know, please go ahead and do that, because I sometimes forget that I'm not talking to you know, there's not someone behind me, but it's on the iPad instead of in person. So just feel free. Anyway, so then we have conserved quantities for this equation, mass, and then we have the energy. And these are conserved quantities. And it's conjectured that that the conjecture is that I'm going to call this 1 is globally well posed and scattering for all U naught in H dot 1/2. So I'm not going to spend real long on this, but I want to at least mention what we mean by global well-posedness and scattering. So what do we mean? So we mean that for all U naught in H dot 1/2, we have a unique global solution, our U of t. Our solution is continuous in time. You know, it's in L infinity, but it also has to, you know, it's continuous. It also depends continuously on the initial data. So we have and then we have scattering, which is defined as there exists U naught plus and U naught minus in H dot 1/2 such that U of t that the H dot 1/2 norm goes to 0 as t goes to plus infinity, or the difference between the free solution and the solution goes to 0 as t goes to minus infinity. But and you could have scattering forward in time or not, but not backward in time, or scattering backward in time and not forward in time. But we're not going to talk about that. We don't think that that's true, or we don't think that that's true in this case. That it should scatter forward and backward in time. Okay, so what would happen if it does not? Then you have blow up. If no scattering, then blow up. And you know, you could the blowups are divided into 2 categories, which is called type 1 and type 2. And by the way, I've seen in other literature, maybe it's for the parabolic equation, sometimes what's considered type 1 in this case is what would be called type 2 in parabolic, I think. So we have to be, you know, careful about how, you know, we have to be clear about how we define it, you know, because it is just, you know, the name is just doesn't really tell you much just from the name, right? You have to know what it means. So we just have our maximal interval I, which is a you know, open interval. And type 1 means H dot SC goes to infinity. And then if not, then you have type 2 blow. The critical norm doesn't blow up, but you could still have failure to scatter, or even failure to have global existence. Okay, so now that we've dispensed with this, we can, I want to talk a little bit about some previous results. And you have, and I'll list them in the order of dimension rather than in the order of when they came out. Yeah, I'm going to do that. So, or I'll list them on the paper in terms of dimension, but I'll list them in terms of when they came out in order. So we have this for D equals 4, SC equals 1, and you have the Rickman. Oh no, this isn't the first. Excuse me. This is why I should have written in dimension. Then you don't have to. So first we have D equals 3. So then in that case, SC is 1/2, and Koenig and Merrill proved that there's no type 2 blowup. And then Rickman and Vishon, when D equals 4, showed that there was scattering. And then in D equals 2, you have SC equals 0, scattering. And then very recently, I think you have a result of, and I think in D equals 5, you have a result by Merrill and Rudniansky and Pierre Raphael and Sudeftel, where there is blowup. That's SC equals 3/2. So yeah, I think that's D equals 5. So yeah, so but then looking back at these results here, where you do prove scattering, or at least no type 2 blowup. I mean, I'm going to go back, that we have this mass that's conserved, right? And the energies that's conserved. So that automatically in D equals 2 and D equals 4 will rule out type 1 blowup, right? Because if the mass is conserved, then you know an SC equals 0 when D equals 2, then you know that the H dot SC norm can't go to infinity, right? And the same is actually true of the energy. When D equals 4, that you do your Sobolev embedding, you have a finite energy, and then that energy must be bounded for all time. So therefore, when D equals 4, you don't have type 1 blowup either. But then you have the result of Koenig and Merrill, where they don't have I mean, they have the momentum, but that's not going to control the H1/2 norm. So they prove no type 2 blowup. So they say, well, if the critical norm did stay bounded, then it would scatter. So we have to ask. So I've been wondering for a long time, actually, about this type 1 blowup, because, well, we know that and we know now that it can happen in 5D, right? But it's reasonable to think that it probably doesn't happen for energy subcritical, I think. And I'll tell you more about, as I go forward, about why I think that that's true. So anyway, well, I'm going to tell you right now why I think that's true. So we have a one line of attack that I guess was initiated by Bourgain, although maybe you would attribute it to the I team, which is Colliander, Keel, Staffelani, Taka, Oka, and Tau, where it's to simply try to use the conservative quantities that we do have to bound the critical norm. So the idea is to start with U naught in a homogeneous Sobolev space. So it's in H, for S bigger than a half, but it's in L2 as well. And you have, so then it's also in the, critical Sobolev space. And you want to look at the conserved quantities that you do have and use them to try to get a bound on this norm, let's say. I mean, right away we know, okay, well, the L2 norm is conserved, so that's good. So we just have to worry about the H dot S norm. Oh, and S is going to be less than 1. So if S is equal to 1, then you're in good shape, right? Because then you would have the H dot 1 norm conserved. And so then by interpolation, you would have the H dot 1/2 norm conserved. And actually, it's even more is true. I mean, not only could you just say, well, the H1/2 norm is conserved and therefore use Collier or Koenig and Merrill's result, but you could actually say that you could actually explicitly calculate the scattering size. And it would be a polynomial function of the energy and the mass, but that's pretty good. You're not going to get an estimate like that from a concentration compactness argument. Yeah, not even close. So anyway, the reason I was kind of not sure who to attribute this method to is because it's called the I method, and this group is called the I team, right? But then you have the results of Bourgain, where he used a slightly different argument called the Fourier truncation method. And actually, this paper is probably closer in spirit to Bourgain than to the I team's work. Although I'm going to keep talking a bit more about the I method. So you just take a function, f, right, in H dot HS, and you take an I operator, IF. And this isn't like if then, right? It's just IF. I thought it was if then when I looked at my notes a minute ago, but it's not. It's IF. And you take a Fourier inverse of a Fourier multiplier. And it's a Fourier multiplier. We suppress the capital N. And we take so this is, you've got that the energy of I U naught is less than infinity, but it's no longer conserved, right? So you have an interesting situation, right? Because you could take a bigger N, and if you do, the E gets bigger, but it also grows slower. It grows more slowly, right? Because if N equals infinity, then you've got an energy that's infinity if you're in this case, but your E would be perfectly conserved. So what happens is you get this kind of tug of war developing between these two things, and the fact that E is big, which is not good, but the fact that it's slowly growing, which is. So there's this tug of war, and the question is, well, which side's going to win? And it depends on the S, right? If S is very close to 1, then you're, probably the fact that E grows slowly, E's not going to get that much bigger for N big, but growing slowly is going to be help, right? But as you get closer to 1/2, the tug of war becomes harder and harder to win for the, to prove, and you would get scattering here too. You wouldn't just get global well-posedness, you get scattering from these results. So as far as I know, the best result at the moment is Qing-Tang Su, where S is bigger than 5/7. So I think Borgana was like 11/13, and then this one was 4/5. I mean, it's and so on. And then in the radial case, you can actually get all the way down to any S bigger than 1/2, but you're really using the radial symmetry a lot in this paper here, really using the radial symmetry a lot. So yeah, it's radial. I'll write radial here. It's still an open question, right? But it's worth pointing out in all of these cases, we're always taking L2 data. So the I method doesn't seem to work as well to estimate the L2 norm, growth, or excuse me, you could design an operator like this, right? Like your Fourier multiplier that, let's say you wanted to take data in H.1 intersect H.S, where S is less than 1/2, right? So then in that case, your energy would be conserved, we would have a finite energy, but you wouldn't have a finite mass. And then you could take a corresponding M, that's called the upside down I method. And it's been useful, but for some reason it looks like in higher dimensions, for a supercritical problem, it's not particularly useful anymore. So, and I guess that's because of the fact that there are blow-up solutions, right? And but I would expect that there would be global solutions for any U0 in H.1/2. I think that's still true. Although again, mainly because of the radial fact that if it's radial, then you're pretty close. Pretty close. Let's say you're pretty close to being halfway done. I'll say that. Okay. Now, then there's another a very analogous problem to this to the cubic NLS, and that's the cubic wave equation. And then, of course, you have to define your initial data and your initial velocity. But it's the same, it has the same scale. So you still have H.1/2, and then this would be H.-1/2. And so there's a recent result which is that you have global well-posedness and scattering for radial U0 in H.1/2, U1 in H.-1/2. But prior to that result, there was another one, which was an intermediate result, U0 in the Besov space, B1, 1, 2, U1 in the Bessoff space B11. So the Bessoff norm, and I like the fact that I have two ones there, so I don't have to worry about getting them in the right order. But it's that the sum, you take your Littlewood-Paley projection, Pj of U naught, the L1 norm, and you put 2 to the 2j here. And that this is less than infinity, and the sum of Pj U1 L1 times 2 to the j is less than infinity. And and Pj is just your usual Littlewood-Paley projection. So yeah, so what's useful about that is that you have you have your Sobolev embedding, right? That Pj U naught L2 is bounded by 2 to the 3j over 2 Pj U naught L1. That's just Bernstein's inequality. And but you have, right, so in other words, this estimate here would imply that your sum of your Pj U naught L2 times 2 to the j over 2 is less than infinity. So you're really you're in a subspace of your critical Sobolev space, but it's a subspace that's invariant under your scaling, right? This norm is also going to be invariant. This norm here is also going to be invariant under the scaling symmetry. So yeah, it's a scale invariant norm, and it's a subspace of our critical norm. Now, and it's radial. So why is that a help, or why was that a help? Before we ultimately got, what we wanted, or I mean, what we wanted for radial data, right? Not for non-radial. That's still open. Well, what happens is you've got this dispersive estimate, right? For so your linear solution, if S of t is your linear operator, right, for the linear wave equation, your linear unitary group operator, right? The L infinity norm is going to be bounded by 1 over t. So whatever problems you have, now we know that it's locally well posed. We know that. That's just I think that's Lindblad and Sog's result. Yeah, so we know that, okay, locally it's fine, but then this 1 over t decay means that you get the worst behavior of your linear solution is right at t equals 0. If you can just get past t equals 0, things are going to get better. And there's an advantage to that. That you sort of have to deal with all the problems all at once, and then after you get past that, then you're in good shape. Yeah, so that's why the Bessoff norm was so useful at least as an intermediate result for the nonlinear wave equation. And so here we prove a similar thing. So theorem, and this is more or less the topic of today's talk, although you have to talk about the precursors too. The cubic NLS 1 is globally well posed. So we don't prove scattering for U naught in W 11 over 7, 7 over 6. And that's a Sobolev space. And what that means is that nabla to 11 over 7, U naught L 7 over 6 is less than infinity. And that's actually scale invariant, right? Because you take your nabla to be 11 over 7, lambda U naught lambda x L 7 over 6, and that's going to equal, well, you pick up 11 over 7 from the derivative, and you pick up your lambda, and then you've got your change of variables formula, and that's nabla 11 over 7 U naught. And then this is just 1. Turns out that's 1. Okay, so now let's go into how we do the calculation for the proof. And it uses the same idea as the wave equation. So, and we want to split it. We have a local solution, okay? And we might as well rescale so that the local solution is on the interval -1 to 1, and you've got a small scattering norm, less than or equal to epsilon on that interval. And you can always do that. No, that's the result of Katzenhagen-Weissler for the wave equation, or for the Schrodinger equation. And so we want to split the solution. So we have U of t we're talking about a strong solution, Okay, now, so we wouldn't necessarily expect to have an energy, but let's of V wouldn't, V is going to be in the same order Sobolev space as U naught, but maybe W could have more regularity, and that's the argument of Bourgain, in a nutshell. And so you take your energy of W, and then you can calculate your energy of W. Now that's not going to be conserved. So, by the way, I've given talks like this before, and I'm going to say that I'm not entirely, this is not entirely how the paper is. There's some technicalities that I'll talk about, but it's one of those things where it's like in golf, right? You give yourself a handicap, and then I guess the idea is that eventually you don't need a handicap anymore. But that's the same idea here. We're giving ourselves a handicap so we can do the problem, and we'll hopefully not need, we won't need the handicap by the end. I don't know if I'll talk about why we don't need it, but we won't need it by the end. So you have this, and after doing some arithmetic, so you can, of course, integrate by parts. And then, no, and the other thing is we're always assuming we have smooth solutions, and then we just, but we take a limit of smooth solutions to get our, distribution, something that's a distribution. So it's standard argument for these. We don't have any of the issues that they have in like Vlad Vaikol is worrying about, where he, is wondering if he, in fact, does get the convergence that he wants at the limit. We're not doing that. Okay, so this is our energy, the growth of the energy. But if we could say that the energy was zero, if the growth of the energy was zero, if it was constant, and put W, let's say W of 1 in H1, then notice we'd be done. We'd be done, because we would want to show that the Strickhart's norm, this L5 norm, we just need to show that that's finite on any compact set. And the contribution of the linear solution is finite just by the Strickhart's estimates. And well, the energy contains the L4 norm and the L6 norm, so therefore the L5 norm is bounded for W. So you just integrate, and you get your L5 space-time norm bounded on any compact set in time. And that's enough to get you global well-posedness. Remember, we're not, as I said, we're not proving scattering. That'd be great. If we could prove scattering, that'd be great. But at the moment, there's some recent results. I can't remember who wrote the paper, I'm sorry, but I apologize if they're in the audience, or even if they're not, but they actually, they assume they're in some Sobolev space that's less regular than that would not embed in L2, would embed in the negative order Sobolev space. And then they have, but the nice thing about their result is that it's that they need less than one derivative on that Sobolev space in order to get the scattering, and then they do get scattering because they're in L2 as well, right? Because they're H dot 1/2, and then they're in a negative order Sobolev space, and they're also in L2. So then they are able to get scattering as well, but we're not assuming we're in L2. We're just in the critical space. Yeah. So okay, so we do our and this one's actually better. This time derivative, because you can integrate that, right? You can integrate a time derivative pretty easily because we're integrating these in time, right? So this term here is actually the bigger difficulty, but it's linear. V is linear, so we have W squared W I delta V. And this is bounded by, well, you just use your Holder's inequality. And this is going to, so for W, the W terms are actually bounded by the energy of W to the 6/7 by the Holder's inequality. And then this one, you use your dispersive estimate, and it's going to be bounded by the norm of U naught W. But look at this 11/7 that we have, right? W 11/7 times 7/6, 7/6, right? Just using your dispersive estimate. but you get a nice 15 over 14 here. So you can use Grunwald's inequality. And that would give you a bound on E. So that's, now there's other terms, and that's, you would integrate from T bigger, you'd be integrating from T bigger than 1. And then there's other terms. I'll just write plus other terms. But those other terms are, you know, the same thing. Not the same exact argument, but it's the same idea. But now I was, to get back, I want to get back to this part here, because I said that you put V of T, and you have W of T, and W is in H dot 1. Well, you don't actually have that. So so you integrate to W of T, where T is between 0 and 1. It's going to be, it's an integral, right? My psi integrals 0 to T, e to the I, T minus tau delta U squared U d tau, right? So how do we put that in L2 or in H1? Well, we have the same issue that we had earlier, right? That we have this 1 over T power. So when T is 0, that's a problem. But when T is bigger than 0, then you should get better estimates. And in fact, you do. So, you know, if you took, you know, the integral from T over 2, if you integrated from T over 2 to T, that's going to give you an H dot 1 norm that's bounded by, you know, something that's some negative power of T. But that's okay, right? Because we really want to know what W of 1 is, right? We're starting our iteration, our solution from 1. We know we have a local solution from -1 to 1. So we start at 1. But then you still have your integral from 0 to T over 2. But the nice thing about that case, when you're integrating from 0 to T over 2, is now this estimate, e to the I T minus tau, is going to give you some nice decay, right? Because there you have nice, potentially, you know, you're going to have nice decay. You know, if it's in, if the nonlinear is in L1, and you know it is, right? Because if U is in H dot 1/2, then U is in L3, so 3 of them is in L1, then you have nice 1 over T minus tau to the 3/2 decay, and you integrate that from 0 to T over 2, where T is less than 1, and that's really good. So you get nice decay, and you can actually get nice decay of a derivative too. You won't be able to put the derivative in L2, but you can put the derivative in L1. And then once you put the derivative in L1, then you also get good 1 over T to the 3/2. Now the derivative in L infinity, and that's perfectly fine too for the purposes of our analysis. So I think this is about where the last talk ended. So I'm going to go ahead and end now. But thank you very much to the organizers and to the attendees for coming to the talk.